Okay, now I'm going to ask you the okay. So, hi everyone, my name is Reinaldo Gonzalez. I'm the president of the second student chapter of the Austral University of Chile, and we are very pleased to have the distinguished Professor David Cooke with us today from the University of Tasmania in Hobart, Australia. Dave, currently the director of Cooke, the Center of Deposit and Earth Science, there since 2017, and he is also director for the Australian Research Council Hub for transforming the mining value chain. He is also an associate editor for economic geology and has made science, communication, and teaching an integral part of his work. His work taking on larger leadership roles and has been in charge of a series of industry-funded research projects, and he's enrolled to becoming a world-renowned expert in magmatic ore deposits. Dave has collaborated with a countless number of geologists, including our professor José Piquer, and he's published over 200 articles on deposits from all over the world. Today, Dave will share a talk with us related to mineral chemistry applied to mineral exploration. So David, the screen is yours. Go on.
Okay. Thank you, Alvaro. Thank you, Ronaldo.
Thank you for being here.
Yeah, it's a pleasure to be here, and thank you all for joining us for this presentation today. It's a real privilege to be able to speak to you all about some of the work we've been doing in mineral chemistry space, which Jose Piquer has been an integral part of over the past few years, and Ronaldo's actually working on this project as well. So, sorry?
No, okay, go on.
Sorry, yeah. Okay, so what I might just do at the start is just put in a little advertisement for the Society for Economic Geologists, because I am the Society's Distinguished Lecturer for 2021. And we just try to communicate to the global community the benefits, particularly for students, of being a member of the Society of Economic Geologists, particularly the education and training courses and the publications and the conferences and early career opportunities that are available to students all around the world. If you are not a member of the Society at this moment, I'd encourage you to apply. There's great conferences coming up next year. We're hoping that the SEG conference will be an in-person conference again in Colorado. The year after, the SEG conference will be in London. So these are annual conferences, and the Society provides funds to support members of student chapters to travel to and participate at those conferences. So I hope you are a member or you choose to become a member, because the benefits are great. One of the things the Society does is it sponsors travelling lecture program. There's the travelling lecturers for 2021. There is going to be a symposium in December where all four of us will be speaking at the travelling lecture symposium. It's probably about December the 10th. And the talk I give there will be a little bit different from the one I'm going to give to you today. So what I would like to talk about today is exploration for porphyry deposits, and particularly using mineral chemistry for porphyry systems. To begin with, though, I would just like to summarise some of the key geological elements for porphyry deposits, because we use these in trying to make discoveries of these giant high-grade resources of copper, gold, and molybdenum. Porphyry deposits typically form in convergent margin settings, such as the Andean margin of South America. So they can be continental arc settings, they can be oceanic island arc settings. Sometimes they form in post-collisional settings. So in terrains such as China, there are places where subduction has stopped, but porphyry deposits still form after the completion of subduction. In all of those environments, the theme that joins the family of deposits together that we call porphyry deposits is the intrusive complex, and it has a porphyritic texture in multiple intrusive phases. So it is located down in the bottom of this part of the Dixilito cartoon we're looking at here. This is a composite multi-phase intrusive stock. It has a porphyritic texture because it releases hydrothermal fluids that produce the ore deposit. So there's an early period of slow crystal growth that causes phenocryst to grow. And then when fluid is released from the magma, the fine-grained ground mass crystallizes out. So that fluid release is what forms the ore deposit, and it also forms the porphyritic texture in the igneous rock. Now, these magmas are special magmas capable of carrying large amounts of copper and or gold and or molybdenum together with sulfur, the key ingredients we need to make porphyry deposits. And what we know is that for the magma to be able to do that, it needs to be very oxidized to allow the sulfur and the metals to be moving together from the domain of partial melting into the upper crust. And the magma needs to be hydrous. It needs a large volume of water to be able to do this. And the best environment to form those oxidized hydrous magmas is in compressional segments of arcs. So magmatic arcs that are undergoing compression or are just relaxing after being through a compressional or orogenic event. These are the places where we get the conditions that set up those magmas. When the fluids are released from the magma, they come out in batches. So there are structural events whereby we break the rock and we form many veins. So we form an overprinting array of veins within and around the intrusion, producing our classic porphyry vein stockwork, such as what I showed you in the first slide. We also produce a series of alteration assemblages, and these are zoned in space, and they are also overprinted in time. So the core of a porphyry deposit early on will form potassic alteration surrounded by a halo of propylitic alteration. Later fluids coming out of the intrusion tend to be more acidic and cooler, and they produce overprints of intermediate argillic or chlorite sericite alteration, sericite or philic alteration, and then a series of advanced argillic assemblages and silicic assemblages that collectively form what we call a lithocap. So this is the lithocap up here with a philic and intermediate argillic root overprinting early formed potassic and propylitic alteration. Now, the details of how that looks varies from deposit to deposit because there's structural controls and protolith controls on those alteration assemblages, but the general patterns of zoning and overprinting are common. And we use these zoning and overprinting patterns to help us explore. Because when we're looking for the ore body, which is typically located around the top of the intrusive complex, we may be coming from high up in the lithocap environment or laterally from the propylitic, or what we call the green rock environment. So it is really important to have these concepts of alteration zonation, sulfide zonation, so the core of bornite and chalcopyrite going out to pyrite, and metal zonation. These are the things we conventionally use to help us navigate from the periphery of a porphyry system into the mineralized center. So metal zoning is something we've known about around intrusive complexes for many, many years. Back in 1927, Emmons published a paper documenting how around the core of intrusions, we see proximal pathfinder elements, elements that are deposited at high temperatures from hot and saline fluids. These are precipitated in or near the intrusion that is the source of the fluids. They are not very soluble. They do not travel far away from the intrusion. So when we see geochemistry dominated by these elements, we know we're getting close to the intrusive center. And then we have a series of distal pathfinder elements which can be precipitated kilometres away from the intrusion, whether that be above or to the side. And so those elements are more volatile, they are soluble in hydrothermal fluids over greater distances, and they precipitate at low temperatures. Now, over the years, we've improved our analytical techniques, we've studied many systems, and so Scott Halley in 2015 and his co-authors published a very useful compendium based on the Yerrington porphyry deposit in Nevada, where they showed the typical geochemical anomalism above a porphyry deposit in the phyllic and the intermediate argillic and the advanced argillic alteration zones. And this is a very useful diagram that gives us many more element anomalism values that we can use to help explore geochemically for porphyry deposits. But their focus primarily was on the roof of porphyry systems, and you can see they didn't show us a lot out here on the flanks. So I want to look in today's talk about what's going on the sides of the porphyry deposits and not so much what's going on above. So the sides of porphyry deposits we have been referring to as the green rock environment, because if the host rocks are volcanic or intrusive rocks, we commonly produce alteration minerals that have a green colour, such as epidote. You can see here epidote replacing K-feldspar phenocrysts in a volcanic rock from the Collahuasi district of northern Chile, and the rock is turning green because of the formation of epidote. So the green rock halo can be very extensive. At El Teniente, we believe the green rock halo to the El Teniente porphyry deposit extends at least 10 kilometres out from the central intrusive complex. Unfortunately, the further away you go, the weaker this alteration gets. So it is a subtle alteration, and very distally, it's made up of chlorite and calcite and zeolites. And then you come in closer and you go to higher temperature and you start to see epidote appearing. So epidote is a mineral very visually distinctive with this colour, forms above about 280 degrees. So when the temperature is high enough, we see a halo with epidote chlorite calcite. We come in closer and actinolite will form. And so this inner subzone of the propylitic halo, this actinolite subzone, forms above 350 degrees and is just outside of the potassic zone where we get biotite and K-feldspar alteration. So actinolite is an indicator of near miss. So mapping the alteration mineralogy in a porphyry district, we do this to help us interpret temperature from cold to moderate to hot to very hot. And where it's very hot, that's where our copper, gold, and molybdenum have precipitated. So mineralogy we use as a proxy for measuring temperature, among other things. Now, the other thing that you can see on this diagram is this shaded area around the porphyry that I've called the pyrite halo. Every porphyry deposit has a pyrite halo, but what we haven't necessarily appreciated as an exploration community is the pyrite halo is more restricted than the other alteration halos. So sulfides precipitate around the porphyry deposit, but we get large areas out here where we don't have pyrite present, except in veins around faults. So large areas without disseminated pyrite. So that's our main green rock halo where we're going to be looking at today. This is a Google Earth image of the Batu Hijau porphyry copper gold deposit in Indonesia. Batu Hijau is a giant porphyry. It's got about 1.6 billion tonnes at about 0.44 copper and 0.44 gold. You can see the open pit. You can see some of the waste rock infrastructure here, and you can see we're in the jungle. If we were exploring for this porphyry deposit, it is eroded down so the intrusions are exposed just below the original land surface. And if we use geophysics, The intrusions are altered to biotite and magnetite, and so there is a magnetic bullseye right in the center of the open pit. This is the open pit here. There's a second magnetic high which relates to some magnetite skarn on the southwest flank of the deposit. So magnetics is a very important exploration tool for porphyry deposits, and under optimal conditions, it can detect the deposit location directly. And that's what happened at Bada Hijau, a very large positive magnetic anomaly associated with biotite magnetite alteration of the intrusion. Geophysics can also detect the pyrite halo. So pyrite will give you a chargeability high, and you can see here we have a ring of anomalous chargeability around the magnetic high at Bada Hijau. And so that is detecting the pyrite halo. So that's basically the limit of how far out from the deposit we get abundant pyrite. There, and interestingly at Bada Hijau, we get a coincident chargeability and magnetic anomaly in the core of the deposit because the chalcopyrite in the core is giving us a chargeability high. That's not normal, but it's very helpful. So you see geophysics works very well at detecting this deposit. If we use whole rock geochemistry, if we took rock chip samples, our rock chip sample geochemistry effectively detects the porphyry deposit to about the same limit as the pyrite halo, because the strong anomalism comes when sulfides are present in the rock. So that's our conventional search radius for a porphyry deposit using conventional geophysics and conventional geochemistry. Our research that we've been doing in the green rock environment is trying to target the mineral chemistry of individual mineral grains, such as these altered mafic crystals here. And what we've been able to show is in large systems, when you do this, you can detect geochemical anomalism up to 5 kilometres from the deposit centre. So we're expanding the detection limit of geochemistry about 40 times over what can be done conventionally by analysing mineral chemistry. So we have a greater capacity to recognise the presence of a hidden deposit buried under cover from further away. So Rio Tinto have been adopting this approach and applying it to exploration. So they've taken that cartoon I've just shown you. They've said, this is the green rock halo going out further than the limits of the cartoon. And we're looking in areas where the deposits have been eroded. And this is what they look like in 3D. And then they're buried under cover. So we've got gravel hiding the deposit. So we can't see it at surface, but maybe we can see some green rocks out on the mountain range sitting to the side of the gravel-filled valley. And the idea is if we sample the green rocks out in the range 2 to 6 kilometres away, can we get signs that this deposit is present here to help us find the deposit? Now, our research program has been done in a series of AMIRA projects that started in 2004, continued to 2021, and we have a new project starting at the start of next year for another 5 years. So industry has been investing in this research where we've investigated a large number of minerals around porphyry systems. We've proved the concept that alteration minerals record subtle hypergene geochemical signatures distal to porphyry deposits. We use laser ablation ICP-MS to get these low-level trace elements of a mineral like epidote or alunite, magnetite, tourmaline, quartz or pyrite. And what it shows us is with just a few analyses, a few rock samples, you can get a sign that there is a large deposit in the district, and you can get tools that help you find your way to discover the deposit. So let's look at epidote. We'll talk about epidote and chlorite today. We won't talk about lots of other minerals, but we've worked on many of them. Epidote is a calcium aluminosilicate mineral. It's a sorosilicate. It has water molecules attached to it. So its major element components are calcium, iron, aluminium, silicon, oxygen, and hydrogen. There is a solid solution between epidote and clinozoisite. So epidote contains iron 3+, so it takes up oxidized iron. It's a signature mineral telling us we have an oxidized fluid, but clinozoisite doesn't have iron 3+, it has aluminium. So there is a redox control on iron aluminium substitution in epidote, and that affects the color of the epidote. There are other elements that can be abundant in epidote, such as manganese and strontium. And when manganese is abundant, the epidote turns pink. Titanium, magnesium, and vanadium can also be fairly abundant. So if you did electron microprobe analyses of epidote, these are the elements you will typically detect with a detection limit above about 400 parts per million. Using laser ablation analyses, you can detect other elements that are present at lower concentrations. And I've listed a series of them here. And I'll note that our database currently contains about 23,000 epidote analyses. So we have a pretty good understanding of the composition of epidote in porphyry deposits now. This graph compares for you the chemistry of epidote in green against the rock sample it was collected from in brown. So on this graph, I've plotted up 7,000 epidotes and 3,000 whole rock samples. And I'm just showing you a series of trace elements that don't like to go into epidote. Their concentration in epidote is lower than the concentration in the corresponding whole rock sample. That means another mineral phase is taking these elements in preference to epidote. And for elements like zinc and copper, it actually turns out they substitute into chlorite. So when you have a rock with epidote and chlorite and no sulfides, commonly the zinc and the copper will be residing in the chlorite part of the altered rock. These elements are not abundant in epidote, but can still be used in exploration. And then there's a series of elements that are concentrated in epidote. They preferentially partition into epidote when we're in the green rock halo, particularly when sulfur isn't present. So if there's no pyrite, we see elements such as manganese, strontium, vanadium, and most importantly, distal pathfinders, arsenic, lead, and antimony, which are enriched by an order of magnitude in the epidote relative to the host rock. That shows you these distal pathfinders preferentially go into epidote. Some proximal pathfinders do as well, such as tin and to a little extent bismuth. Even though the concentrations are low, they're definitely going into the epidote structure. So how did we work out how to use epidote in exploration? Well, we were working in a couple of places, and I'm going to show both of them to you. First, we're going to the Baguio district of the Philippines. Then we're going to the Collahuasi district of northern Chile. So in the Baguio district of the Philippines, what we have is a series of porphyry and epithermal deposits that are 3 million to 1 million years in age. So this is a very young district associated with subduction of the Scarborough Ridge underneath northern Luzon. We have flat slab subduction or low angle subduction that's produced a series of adiabatic porphyry magmas and a number of porphyry copper gold and epithermal silver for gold veins and some skarns. This is the central Baguio district, and we're looking from west to east. In the foreground, we have a skarn prospect at Mexico. In the floor of the river valley, we have a small porphyry copper deposit, Black Mountain, which has 2 ore zones. And then this area of landslides is a large porphyry copper gold deposit called Nugget Hill that has not yet been mined. Down over to the side, a series of intermediate sulfidation epithermal veins. So this is a plan view of the Baguio district, and you can see here's the Mexico prospect, the skarn with its pyrite halo, the Black Mountain porphyry with its potassic zone and a pyrite halo, and another skarn, Thanksgiving, next to it, the Nugget Hill prospect with its potassic zone and its pyrite halo, and then intermediate sulfidation epithermal veins, for which Baguio is famous, 7 million ounces from Akupan, 10 million ounces from Antamok, high sulfidation state veins at Kelly and Chico, and a very large lithocap extending north from Nugget Hill towards Baguio City. So overall, about 40 million ounces of gold and about 4 million tonnes of copper in these porphyry and epithermal systems. We're going to take a look at a transect between these three discrete prospects, the Skarn prospect and two porphyries. So the central Baguio district here. This is zooming in now. You can see the Pyrite Halo is outlined in blue. There's the potassic core at Black Mountain, a series of diorite and dacite intrusions. And we're going to look at samples collected on two transects from Mexico to Black Mountain, Ken ore body, and from the southeast ore body at Black Mountain to Nugget Hill, going along Lulu Creek. So in both of these transects, we go from the potassic zone into the Pyrite Halo and then into the green rock halo and back into the next deposit. So we can compare different deposits. The types of modes of occurrence for epidote, we have epidote inside the Pyrite Halo where we see pyrite veins, D veins that are weathering here, as you can see. So there's both epidote and pyrite present in these rocks. There is skarn, so we have epidote in epidote garnet skarn, where we have carbonate host rocks. And then we have classic green rock alteration of epidote carbonate, hematite chlorite, but no sulfides. So this is outside of the Pyrite Halo. These are the type of rocks we analysed. And what we did was, here's a rock from outside the Pyrite Halo. It is a lamprifier It has hornblende phenocrysts, which are very fresh, and it has a ground mass, which is fresh, and it has a very thin epidote calcite vein cutting through it. And what we're looking at here, these circles are where we've gone and done laser ablation analyses. We're going to zoom into this one, where you see there's a hornblende crystal cut by an epidote calcite vein. And effectively, for geochemical exploration, this bit with the vein is useful, and this is useless, because none of the geochemical anomalism of the porphyry fluids are affecting this rock. It is unaltered. So all the useful exploration geochemistry is in this tiny little vein. If we do a bulk rock analysis, we dilute the anomalism with the useless rock. But if we target the minerals in the vein, we can detect the anomalism quite strongly. So let's zoom in, look at a microscope photo here. This is an SEM image, and you can see we have hornblende crystal with cleavage cut by our epidote calcite vein and then a ground mass with a bit of magnetite in it. And you can see these holes are laser ablation spots. And what we do is we burn a hole in and we ablate the epidote and we measure the trace element chemistry. We can also do line analyses where we burn the laser across and we can generate chemical maps of the element distribution. And if we look at a laser ablation map here, what we can see is all of the arsenic is in the epidote and not in the calcite and not in the hornblende. So all three minerals are in this map, and you can see 100 parts per million arsenic in epidote, 50 parts per million antimony in epidote, about 100 parts per million lead in epidote as well. And just showing some of the other elements to help you see the distinction between the epidote, the calcite and hornblende. So this confirmed for us that epidote is taking these pathfinder elements into its crystal structure. Then we can look at this data in space. And so what we can see here is when we take our sample transect AB going from Mexico to Black Mountain, we can plot our samples there, and then we can go Black Mountain to Nugget Hill and plot our samples there. The red dots are whole rock data. The brown are skarn epidote, and then the triangles are epidote from green rocks. If they're filled, they're from veins. If they're open, they are from the altered wall rock. And you can see that the whole rock geochemistry of arsenic was pretty low across the transect, apart from when you come to the Pyrite Halo of the big system at Nugget Hill. But the arsenic in epidote is much stronger, and you can see a really strong arsenic anomaly around the Nugget Hill porphyry by analysing the epidote. But you can't see it if you analyse the whole rock because of that dilution effect. So this is interesting. We can see we've got our footprint at least 1 kilometre further out from the big porphyry at Nugget Hill, And the small porphyry and the small skarn aren't giving us strong anomalism. So we're seeing both a larger footprint of geochemistry and distinction between the fertile system and the weak systems. So maybe the mineral chemistry is telling us about fertility as well as giving us a bigger search radius. So let's quickly look at some other elements. That's arsenic. Antimony does the same thing. You see no antimony anomalism in the whole rock with the red circles, but a strong antimony anomaly in the green rocks. And there's lead doing the same thing, a lead anomaly on the edge of the pyrite halo, but an extensive lead anomaly in the green rock that we can't see in the whole rock data. Surprisingly, some other elements do some strange things, like zirconium is enriched in Epidote just on the flank of the Black Mountain porphyry. So when looking at all of that, across Baguio and other systems, we realised that the system was going to be, that the systems have a consistent pattern of behaviour, but they can't, sorry, I'm getting interrupted. Sorry for that. The systems are basically showing us a common pattern of behaviour of element dispersion, and it's affected by what minerals are co-precipitating with the epidote. We have, in the potassic core of a porphyry system, high temperature conditions, deposition of copper sulfides and gold. Other metals are too soluble to precipitate. Calcium is being leached from plagioclase, it's being leached from hornblende, and it's being dispersed out of the potassic zone into the green rock halo. Epidote's not stable in this environment. As we move out to the pyrite halo, we go into an environment where epidote and pyrite are co-precipitating, and there's competition between the epidote and the pyrite. And what we get is precipitation of epidote with unusual chemistry, such as high rare earths, and the pyrite is scavenging the base metals. And then when we run out of pyrite, we get our green rock halo, where arsenic and antimony and lead are precipitating into epidote. Manganese is also going into epidote and substituting, and the pyrite halo, the pyrite is not present. So what we've also found is that the highly productive porphyries are fluxing the most metals. Okay, so that's one of the learnings from Baguio. And I can show you that also with Collahuasi. So let's take a look at Collahuasi in northern Chile. This is a map of the Collahuasi district. We have three very large porphyry deposits. The biggest is the Rosario porphyry, a hybrid porphyry and high sulfidation deposit, the giant Quebrada Blanca deposit, and then the large Ujina deposit. Okay, so these are monstrous copper moly porphyries, and we've done green rock chemistry across this entire district looking at the footprint of these three deposits. Interestingly, the best story we have is out of Ujina, where we have the best coverage of samples, well, I'll show you chemistry from all three. But let's focus in on Ujina. You can see our sample distribution at Ujina was going north to south from the potassic core through the green rock halo. This is Tim Island's mapping of the alteration around the three deposits. But we have a pretty extensive suite around Rosario and Quebrada Blanca as well. Rosario is complicated by the fact that there's a strong high sulfidation overprint in the La Grande area, so more acidic conditions, and that affects the green rock chemistry. You don't get so much green rock. But Quebrada Blanca has a very big green rock halo around it. If we just look at Ujina, and what I'm going to do is we're plotting the distance to deposit center. So this is the center of the deposit, and we're looking at the chemistry of these samples out from the deposit center for 5 kilometers. And you can see the epidote is in red and the whole rock is in black. So the whole rock chemistry is detecting the Ujina porphyry quite nicely up to about 1.5 kilometers away. There's an epithermal vein 2 kilometers out that the zinc is picking. And the epidote chemistry is really subdued. These are our classic pathfinder elements we use for whole rock geochemistry to find a porphyry deposit. There's our footprint, getting anomalism within 1.4 kilometers of Ujina using rock chip sampling. Here's the elements that are affected by potassic and propylitic alteration. And again, you see the epidote chemistry is low. I haven't put calcium on. And the potassium addition with the potassic zone, the sodium and the calcium depletion with the potassic zone, we can see that again about 1.4 kilometres out from the deposit. Now, if we look at arsenic in epidote, or antimony in epidote, or lead in epidote, everything switches here. The geochemistry in the whole rock is very subdued, but the epidote chemistry is really strong and really anomalous. And you see the strongest lead signal is actually coming 5 kilometres away from Uhina. We haven't actually sampled the lead to background, whereas maybe the antimony we've sampled to background. You can see it has a spike and then it decreases, and maybe the arsenic is sampled to background as well. But the footprint of the Uhina green rock halo goes more than 5 kilometres based on epidote chemistry. And you can see this is the sort of anomalism we're seeing in epidote. Large areas of more than 25 parts per million arsenic, 10 parts per million antimony, 100 parts per million lead in epidote. And let's zoom in on the arsenic, just highlighting, the whole rock is really flatlining. There's a large number of arsenic greater than 25 in epidote, going 1 to 3.5 kilometres out from Uhina. And there's areas where there's a lot of arsenic greater than 100 parts per million out from Uhina and distal to the deposit centre. So this is interesting because one of the things we've learned is the really big deposits have very strong anomalism in arsenic and antimony and lead, and that the strongest anomalism isn't close to the deposit, it's far away, which is great for district scale exploration because it means you can say, oh, I'm getting a very strong signal. That means there's a porphyry in the district. I'm probably not close to it, but maybe I can look at how that composition changes as we approach the deposit. So here's some other pathfinders from Collahuasi. You see that tin has a proximal signature just outside the potassic zone. So does bismuth, so does uranium. Anomalous in epidote, close to the deposit. Yttrium, manganese and strontium, a bit more similar to arsenic and antimony, the more distal signatures. So what I'm trying to show you here is that as you go from distal to proximal, the chemistry of epidote is changing. So you can use the different pathfinder elements to navigate towards the deposit centre. Distal, strontium, lead coming into manganese, arsenic, antimony, then near miss, uranium, bismuth, tin, and even zinc, and a little bit of copper and moly. You can't see it there. This is what the arsenic in epidote looks like at a district plot. So you see the Uhina has a nice strong arsenic halo, but compared to Quebrada Blanca, it's subdued. Quebrada Blanca is a bigger deposit and it has a much stronger arsenic in epidote signature, getting up towards 0.28%. Rosario is a bit more equivocal because of that acid alteration. So the strongest signature here is the actual Quebrada Blanca system, and the values are strongest distal and they get weaker proximal. Here's antimony doing the same thing. We're getting up towards 0.2% antimony in epidote around Quebrada Blanca as well. You see a much stronger antimony signature around Rosario. And when we put antimony and arsenic together in epidote, what we've found is that metamorphic epidote has very low arsenic and antimony, so it plots to the bottom and the left. And the biggest porphyry deposits like Rosario and La Grande, they have really strong antimony arsenic signatures, so they plot to the top right. So we can use this diagram as a bit of a fertility tool. The big deposits have epidote, distal that plots in the top right, and proximal, they plot down here. The small deposits, they all plot down here, and metamorphic plot down here or don't even plot because the antimony is below detection limit. All right, so that's epidote. I want to briefly jump over to chlorite now, which is another green rock mineral we use. This is now looking back at Bada Hijau. And this is the Bada Hijau open pit, the potassic core. Here's a sample transect going 5 kilometres out from Bada Hijau. And what you're looking at here is chlorite chemistry. And we're looking at the ratio of titanium over strontium in chlorite. And you see it changes on this transect of brown dots 5 kilometres out from the deposit, 2 kilometres out from the deposit centre over 4 orders of magnitude. Now, the key message here is this is only visible in chlorite. If we take the whole rock data, these are all basaltic andesites and their titanium-strontium ratio is constant. So this very strong anomalism is detectable only by analysing chlorite close to this deposit. And then we get out to background chlorite compositions which mimic the whole rock trend. So basically what you're looking at here is chlorite chemistry going out 2 kilometres away from the deposit centre, giving us a strong vector. And it's such a good correlation that you can fit a regression coefficient to it and come up with a relationship that predicts distance to the deposit centre from the analysis of titanium and strontium in chlorite. We call this a proximity ratio, and I'm going to show you how we use it in a minute using a different example. Here's an example from Taldi Balak in Kyrgyzstan, where we've put epidote and chlorite chemistry together. We have 30 samples across the district. So that's a sample spacing. There's a 500-metre space. Here's the outline of the deposit based on the soil geochemistry. And you're looking at a low arsenic in epidote domain and a high titanium over strontium in chlorite domain, giving us a coincident anomaly that defines where this deposit is located. So 30 rock chip samples across an area that's about 6 kilometres by 3 kilometres in dimension would effectively discover the Taldi Balak porphyry just from sampling epidote chloride in rocks like this. So let's now go to one last example showing how this can be applied in exploration. So we're looking at the resolution porphyry deposit in Arizona, and this was given to us as a blind site test. The blind site test involves basically companies giving us samples where we don't know where they're from. They have an internally consistent sample coordinate set, but they relocate the sample so we can't work it out from Google Earth as to what we're dealing with. Resolution is a giant high-grade porphyry copper molybdenum deposit. It is basically a laramide age porphyry, and it's buried under cover. So these are tertiary volcanic rocks overlaying Paleozoic and Proterozoic rocks, and buried back in the hillside is the resolution porphyry in a Cretaceous half graben that is not exposed. So looking past that ridge line, resolution is buried under the tertiary volcanics here. There are a large number of epithermal veins exposed in the range around it, but the porphyry itself is not exposed. It was discovered when they were mining the magma high sulfidation copper silver deposits, and they drifted south and did some exploration drilling. This is the cross-section I'm going to show you samples from, and you can see the sample locations. These are the samples that were sent to us. They were just outside the resolution ore zone, and we're going to see them projected onto this geologic cross-section, but you see everything here is tertiary cover. We can't see the resolution porphyry. We were sent 12 rock samples, and they were all green rocks, okay? So you can see here epidote chloride alteration. One sample had an epidote vein, none of the others had epidote veins. So we just replaced them. And the epidote has a subdued signature. So when we plot on arsenic antimony plot, it wasn't like Collahuasi. It wasn't plotting like a giant with very high arsenic antimony. It was plotting like a small deposit, like Black Mountain in the Philippines. But this is also where the epidote plots when you're close to a giant system. So when we looked at this data, we said, is it small or are we close? And the geology tells us we're close because we have coexisting epidote and pyrite. So here's an epidote laser ablation map from resolution. And you can see, if I zoom in on the arsenic, the antimony, and the lead, they are present in the epidote, but they are low. They're not as abundant as in the example I gave you from the Philippines. The thing is, these are coexisting with pyrite. And when pyrite is present, and here's a pyrite map, you can see it preferentially will take up the arsenic and the lead. There's competition for these chalcophile elements and these metalloids between sulfur and between epidote. Now, this is where our samples came from at resolution. And this is our sample distribution in cross-section. And what you're now looking at is titanium over strontium in chlorite. All right, so we have one drill hole that's very deep, and we have several drill holes that are not so deep at two ends of this cluster of samples. And you notice that titanium in strontium is getting hotter and higher, deeper. So we've basically shaded the bubbles. Each bubble is shaded on the value of titanium strontium. So it's bigger and it's hotter when the titanium strontium ratio is higher. And a higher titanium strontium ratio implies proximity to the deposit. Now, if we calculate a distance to deposit center using a chlorite proximeter, so here we take the Bader-Hijau equation, we'll take those 10 samples of chlorite and we predict how far we are from the deposit center. On a 2D section, it's a circle. Basically, the distance to deposit center from this point is that far away based on this proximeter. And so if we do that for every one of these samples, what we see is they actually have a point of convergence in between and below the sample cluster. So we were able to say to Rio Tinto, we think it's a big system. The epidote is subdued because we're close, but the chlorite is giving us a very precise target. We think drill deeper and drill below the sample cluster. And this is actually the geology of resolution. This is the cover. These are the drill holes. These are our sample locations. This is the ore zone, and this was our target. So we overshot the target, but they would have had to drill through the ore body to hit our target. So Rio Tinto were very, very happy with this result because we were basically predicting the location of a giant porphyry deposit undercover using 10 chlorite samples. Okay, so that's an excellent result. Rio Tinto then validated the test. They went back and collected additional samples and used their laboratory rather than our laboratory. So this is a 3D view. There's the resolution ore zone. There's the drill hole assays. There's their sample location. So they're pretending they didn't know this was there. So this is what they would have got taking those green rock samples. And they did things in 3D rather than 2D. So they calculated spheres, and their spheres coalesced at the same point that our circles did, predicting again the location of the deposit very accurately using chlorite chemistry. So basically, what I hope I've shown to you here with those examples is chlorite and epidote are distal alteration minerals that form around porphyry deposits. They provide us with new tools that give us information to help us vector towards the deposit center, particularly chlorite, and to assess the fertility of the district, particularly epidote. And we can do that across a range of rock types. We are getting into using dating of these minerals and data analytics, and that work will be publishing soon, and is showing significant enhanced potential to basically identify these distal footprints. And what we're hoping for is that one of these days, someone is going to be applying these techniques and be able to put their hand on their heart and say, this green rock mineral chemistry approach contributed to the discovery of this porphyry deposit. We haven't achieved that yet, and part of the barrier is the technology is not available widely to companies. It's locked up in university laboratories, but we think that will come soon. So thank you to all of the researchers over the years. There's been a huge team putting this together. I'm just speaking on behalf of them. And thank you all for listening to the presentation. If you have any questions, I'm very happy to take them.
Well, David, thank you for such an amazing lecture. If someone has a question, you can write that on the chat box, or if you prefer, you could use your mic. let me know.
Thanks, Irene. Good to see you.
And talk, Dave.
Hi, Irene.
So Alexandre's got his hand up, I believe. Would you like to ask a question?
Yay.
Hi there, can you hear me?
Yes, you can.
Well, I can stop my video and see. I'm here. I had a
You can,
further.
Alex.
Can I do it now?
Yes.
Right here. Here from home. So yeah, I had a couple of questions. Thanks for the talk, by the way. Well, I'm not an expert in the field, so but I hope you can understand that it's very interesting for every person interested in geology in general, and in particular in geochemistry. You show various diagrams showing a positive enrichment, or positive anomalies in various elements like arsenic, antimony, lead, and when we in Epidote, when we get closer to the fertile source, and so there is an enrichment, but at the same time you see a range of contents from high contents to low contents. And so I was wondering, does it mean we're seeing various events of Epidote formations, or how do you explain this range of contents, basically?
Yeah, so I actually, the variability is an inherent part of mineral chemistry. I actually had a slide on that, which I took out. Basically, when we do laser ablation of an epidote grain or a chlorite grain or whatever we're drilling through, we drill through different growth zones. So we're drilling into the grain and we don't know, it's like drilling for exploration. You don't know what you're going to drill through, but you are drilling through different growth layers. And as we do that, we get variability in the composition within the grain. And so when we analyze different spots and we're analysing different parts of the grain, we see that variability. And for some elements, like if for calcite, I can get 5 or 6 orders of magnitude variability of rare earth elements in the individual grain, right? So it's huge variability, and it's real, it's geological, and it relates to process. Okay, so sometimes what's effectively happening is we just have hot water precipitating out the mineral with no trace element anomalism, and sometimes we have really fertile precipitation of metals and all sorts of things going into the mineral. So those highs and lows are a natural part of laser ablation analysis, and that's why when we do the analyses, we might have one rock sample, but we'll do about 30 spots. We've done quite a bit of work to try to work out what we need for reproducibility because of the variance in the data. And you need to go about 25 or 30 spots just to allow for the fact that there are high flyers and there are low flyers, and you get quite a big range. So that's been a fair amount of effort to get to the point where we're comfortable with the number of analyses we should be doing. And yeah, it's process. The other thing that we found in more recent times is the variance in the data is an expiration vector. So distal to the deposits, we see low variability, and as we come in close to the center where there's multiple batches of fluids, multiple paragenetic events, multiple stages of growth, the variance is much higher. So we're actually looking at variance from a data analytics perspective as a tool to aid in detection of deposits. You get closer to the center, they're more complicated, the mineral chemistry is more variable. Hope that answered your question.
Yeah, sure, thanks.
Okay.
And I had another question, or more like a comment. You mentioned the correlation of the titanium strontium ratio in chlorite as a good indicator of distance from the source, and you apply this correlation to the last case you show us to try to estimate the distance, the potential distance of the the porphyry. I was wondering if this correlation was only valid for one specific case and not, you couldn't apply it to whatever case you want. And especially with the result you show us that you were overshooting the distance, maybe that's a confirmation that the titanium strontium ratio, yes, it's a correlation, but it's a qualitative indication of the distance and not really a quantitative assessment.
So Alexandra, yeah, no, you're quite right. We've in the research program we've done, we've worked on about 70 porphyry deposits now to test this. And what happens is titanium strontium ratio, so chloride is sensitive to temperature. And I didn't really go into this in the talk because of time, but high titanium is going in at high temperatures. And this is true of quartz, this is true of zircon. Titanium is a temperature indicator. And then elements such as strontium and lithium, they're going into chloride at low temperature. So when we ratio them, we're basically enhancing the signal to noise ratio, and we're trying to ratio elements that are high temperature and low temperature pathfinders. So that titanium strontium ratio is effectively a geothermometer, but the size of the intrusive complex, the size of the thermal anomaly impacts on that titanium strontium ratio. The slope of the line changes. So at El Teniente, we get a very flat, broad line. At Batu Hijau, we get a sharper line. We go to Black Mountain and it's a really sharp line because it's the gradients, the thermal gradient that we're mapping. So we've put out a series of those proximity ratios for different size porphyry deposits. In the special issue last year that we put out in economic geology, there was one for El Teniente, another one for the Collahuasi district. There's one for Batu Hijau. There's one for North Parks. And so you can use a range of them and say, well, okay, we don't know what the size of the thing is, but if we looked at this proximity ratio, it predicts this distance. And if we look at this, it uses this distance. So that was sort of where that's the stuff we put out in the public domain. Where we're currently working is using data analytics. So we're going a lot more into being data driven and letting each system's data set drive its own story. And we've developed some software that lets us actually interrogate this in 3D. So we'll talk a little bit about that at the SGA conference next year. But that's proving really powerful. And so we think the stuff I've shown you is sort of the thought process that has got us down the path, but we've moved a bit past that, precisely for the reason you've raised, is that each system's got to be treated on its own merits, and it's really hard just to say, okay, I'm going to take a Batu Hijau equation and I'm going to apply it to Serra Casale. Doesn't work, okay? Or it might work by coincidence. It turns out resolution and Batu Hijau, they're very similar in their behaviour, and they're very similar size. They're both about 1.6 billion tonnes. So the size of the intrusive complex is probably comparable for thermal anomaly. Okay, now Ricardo, I see, has asked a question in the chat. Could the chlorite proximeter be used to estimate hotter places where chlorite was formed in intrusion-related precious metal systems? So some of the research we've been doing in more recent times has been taking epidote and chlorite into different environments. So we have worked on orogenic gold deposits. We've worked on ISCG deposits, sediment-hosted copper deposits, epithermal deposits, skarns and carbonate replacements, and we do find it's working in these environments. There can be some peculiarities of the individual systems as to different metal associations. So ISCGs are giving us some different flavours to their epidote and chlorite, but we are still finding there's applicability of this technique. We did a study of the Hemlo gold deposit in Canada, and Hemlo, well, you can argue what Hemlo is. It's a giant Proterozoic gold deposit. Some people think it's a metamorphosed alkalic porphyry. Other people think it's orogenic gold. Other people think it's intrusion-related gold. We went and did a sampling of an area of about 15K by 7K, and the epidote, chlorite and pyrite light up the deposit beautifully. So we were expecting a really tight halo around the shear zone, and we got a footprint that went out 4 kilometres out from the main controlling structure. So we're very encouraged by that. So most of our research has been in the porphyry and epithermal space, but the work we've been doing in other environments gives us great encouragement. The problem that you face with this stuff is sampling to background. And I know when we started, we were thinking, oh, maybe we'll sample a kilometre out from the Pyrite Halo. We weren't really sure what we were doing. When we went to El Teniente, we sampled 10 kilometres out. We still hadn't got to background. And I think if you go up to Candelaria and try to do it in the Candelaria district, you'll have to keep going even further out, because I think the ICGs have enormous footprints, and getting to background is a huge challenge to work out, because they can basically be a base of the background. Anyway, hopefully that answers your question, Ricardo.
Thank David. I have a question.
Sure.
Cladding the blind test like Coyahuasi, Batuhayu, if you have obtained results applying this technique mineral chemistry on greenfield exploration.
Mm-hmm. Our laboratory is doing commercial work for industry all the time in greenfield exploration. In fact, I know a company, we just did a commercial job in Mexico, and a company, Almadex, just put out a press release saying, oh, look at the target they've identified. It's coincident with a big IP anomaly we haven't tested. So they're about to go off and drill it. So they're actually, I'm hopeful they hit something, because if they do, they'll be happily saying this helped us discover a porphyry deposit, which is what I'm hoping to see. So Rio Tinto, Codelco, BHP, Anglo-American, Newmont, they're all sending material to us to analyse or to other laboratories, because commercial labs such as ALS and Bureau Veritas, they're not doing these analyses. So it is being applied in greenfields exploration. The companies don't always share. Yeah, that's what I thought, Randy.
Thank you.
Yeah. Okay, so Saul, your question about analysing propylitic with other alteration, the question also gets asked about what about weathered samples? So here's the thing, mineral chemistry, we're analysing a specific mineral. If that mineral gets altered or weathered to another mineral, then you're not analysing it. You can tell straight away. People sometimes send us what they think are green rock samples with epidote and chlorite, and they have a green illite or a green spectite. They've just seen a green mineral and they've said, oh, well, give us an analysis. We say, well, we can't, because you haven't sampled epidote and you haven't sampled chlorite. We could do an illite analysis for you. So that's the beauty of the green rock approach, is you're targeting the hypogene alteration mineral, and the hypogene geochemical dispersion halo is encapsulated in that alteration mineral. So once that mineral's altered, that geochemical signature is lost, but you don't analyse it. Right, you're analysing a different mineral and getting a different geochemical story. So the key thing here is you're analysing, you're targeting a specific mineral for the approach. Now, I did mention that Rosario, the green rock chemistry, is a little different, and that is because there is propylitic alteration at Rosario, but there's a more acid environment, and that changes the epidote chemistry. So actually the highest copper we've ever seen in epidote is from Rosario in Coyahuasi. So that more acid environment, we're seeing copper get into epidote. So there are peculiarities. Now, Alexandra, yes, Jose would love a laser ablation system. We don't have an old unit that's not, all our lasers, we've got 5 laser ablation mass specs, and they're in continual operation. So there are workhorse. We use them not just for this green rock stuff, it's for our dating, it's for our trace element deportment, our geometallurgy. So I think if Universidad de Austral can get a laser ablation facility in place and operating, you will have a really key resource for South America in your university. And I think, there's a lot of work going on, not just by our group, by plenty of groups around the world that are demonstrating just how powerful a technique it is. So I really hope you do get your facility up and running soon.
I have another question. In Coyahuasi district, Rosario, the Rosario porphyry, has overprinted by a high epithermal sulfidation deposit.
Yep.
And commonly, this kind of deposit has anomalies of arsenic.
Yep.
So how this can affect the anomalies of arsenic in Epidote if you have overprinted process on the Epidote related to porphyry.
Okay, so I will share my slides again, just briefly, if that's okay, to help answer this question. Okay, so right back towards the start of the talk, oops, that's gone to the wrong slide. Bear with me. I don't want that slide. I want this slide. Okay, so I talked about Scott Halley's work on geochemistry. Now look, in the whole rock geochemistry space, you can see Scott is showing here that above a porphyry in a lithocap, the advanced argillic zone, which is where high sulfidation occur, the whole rock geochemistry of arsenic is 50 parts per million and greater. That's the anomalism we expect to see. What I've just shown you in the green rock zone was the arsenic was below detection limit. It was below 2 parts per million. So the rock geochemistry arsenic is below 2 parts per million, but the epidote was getting up towards, in extreme cases, 0.2 weight% arsenic in epidote. Here, the arsenic is in sulfides. So it's in the pyrite in the lithocap. And so when we look at the Rosario district, the high sulfidation veins have really strong arsenic and antimony anomalies associated with sulfide alteration. The epidote that forms distal to those is also enriched in arsenic and antimony, but it's also enriched in other strange things, such as copper. But yeah, there's heaps of arsenic and antimony in that system, but there's also heaps of sulfur. And so the arsenic and the antimony wind up in pyrite, they wind up in energite, tennantite, leuceinite. There's a whole bunch of sulfur-bearing minerals that they are bonding with. And it's only when you run out of sulfur and you start making epidote that you get the arsenic going into the epidote. Okay, does that help? Ronaldo, explain?
Yes, just perfect.
Yeah, excellent.
Yeah, if there another question, so I don't see. So, Alvaro, can you close the talk?
Yeah. If there are no more questions, I wanna thank you again, David, for being here today with us, and I hope to see you in another time in the future.
Fingers crossed, I'm coming to Chile next October. I've been asked to come to the International Association of Applied Geochemistry Conference, which is hopefully running in Valparaiso in October, and I'm very much looking forward to coming back to Chile.
October of this year?
Next year. Next year. So 2022 in Valparaiso. The International Applied Geochemistry Conference is happening in Valparaiso.
Oh, great. See you there. Yes. Well, thanks for being here, and the results of your work have been a great contribution to the science of economic geology. So it's an honor to be here with you speaking about your work. So thank again, and
Well, thank you.
goodbye everyone. Thanks to the participants for attending, and see you another time.
Okay.
See you. Bye-bye.
Thank you all.
Bye.
Bye. See you in Chile, indeed. Thanks.
See you.